So today is 10/21/15. The first thing I want to say to you is I want you to appreciate how hard it is to pretend to not know something that you already know. And you have experience with this if you've ever known a secret that you shouldn't have known, or if you've ever known about a surprise party that you shouldn't have known about. It's really hard to pretend you don't know something that you do. And it's kind of hard to imagine how your brain was before you knew it. So it's really hard for us as modern Western people to get how little was known about what stuff was made up of. It's almost impossible for us to not, you have known since probably the 3rd grade that the whole world is made up of little tiny particles that are moving all the time. Right? It feels like you've always known that. So it's so alien to think about not knowing that. It's such a weird question to ask, well, what's stuff made of? Because you all go, oh, little particles, they're called atoms, they move around. And the kid who I've had in the 9th grade physical science class who has paid the least attention through 9 years of school up to there can generally still answer that. Yeah, stuff's made of little particles. They move around. They're called atoms. Like, they may not know the subatomic particles. They may not know that protons have a positive charge. But they know that things are made of atoms. It is almost impossible to imagine a world where we don't know that. But that is, in fact, the world that existed. And we're going to start off with Democritus, this guy. So Democritus lived between about 460 and 370 BCE. That's before Common Era. So that's the numbers that run backwards, the confusing ones. And Democritus was a philosopher. He was a scientist, but in this period of history, science and philosophy are not that different. And he was thinking about what stuff was made of. And actually, you found, a lot of you in your reading, that his teacher, and I always screw up his name, Lepicus, anyway, another Greek guy, probably really started to formulate a lot of these ideas. Democritus gets the credit because he wrote more about them, though most of his writing was lost. So in his sort of thought experiment about stuff and what stuff is made of, he thinks, okay, if you take a lump of bread or a lump of clay and you cut it in half, and then you cut those pieces in half, and you cut those pieces in half, etc., 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 there's going to come some point where you can't cut it in half anymore, or it stops being clay or bread or gold or rock. So it becomes this uncuttable thing, this thing that you can no longer divide. And he calls this idea atomos. And it's from the Greek. And a means un or without, and you're familiar with that. Amoral, atheistic, give me another one. I don't know. But a, without or un, and tomos in Greek is cuttable. So this is literally the uncuttable. It's from, we very often say it's from the Greek for indivisible. Yes, there is some confusion on lots of presentations about the word indivisible and the word invisible. You might want to address that. Democritus says atoms can be any size, they can be any shape, they're indestructible, they're solids. And this is all philosophical. He did not invent the atom. Democritus did not discover anything. Democritus did not invent anything. He merely proposed a philosophical way of understanding the matter around us. So this is not grounded in any kind of physical reality. This is his thought process. And actually, if you look at illustrations from the writings of his that do survive of what he thought the shapes of atoms were, because he assumed that the shape of the atom made the material have its characteristics. So, like atoms of iron had hooks in them because iron stuck together so strongly, and atoms of water, because of course he didn't understand compounds. He didn't understand any of that. Like atoms of water were slippery and flat because they could flow past one another. So it's kind of crazy stuff. But again, it's not science. It's philosophy. And it's grounded in just thinking about the world, not any kind of experimental evidence. Okay, well, but still, he's on the right track that all matter is made up of little pieces, that there's some kind of little piece at the base of everything. Well, sadly, Democritus apparently was not as good at PR as he should have been. So Aristotle comes along, and if you've heard of 3 Greek philosophers, they are probably Plato, Aristotle, and Socrates. Those are the 3 that roll right off the tongue. People know them. If we went out on the street and tried to ask people, name me a Greek philosopher, Aristotle would probably be one of the ones that popped up right after, I don't know. So he comes a little bit later than Democritus, because remember, again, the numbers are running backwards. And, yeah, which confuses people. So he lived roughly 384 to 322 BCE. He thinks this notion of some sort of little undividable particle is ridiculous. And Aristotle actually writes a lot on the nature of being and the nature of matter. And a lot of his writing survives. So, history is written by the winners. Ancient history is written by those whose stuff survives. If you burn all of your enemies' books, you have just guaranteed that they will not get their place in history. And nobody burned Democritus's books. It's just a really long time ago. But Aristotle completely dismisses this idea, and it was called the atomists by later people. So, again, he has all these writings on the nature of matter, and what he says is that everything in the world is made up of 4 elements: earth, air, fire, water. And he has a 5th. Ether is how it's usually said. It's usually pronounced ether, but it's spelled aether, and I don't know if that's a translation from the Greek or what. And that matter is continuous, meaning it can't be divided ever. And he actually feels very strongly about this on religious grounds. And remember, we're dealing with an ancient Greek here. He says, if the gods so choose to divide anything, they can. So he says that there's never any level at which something cannot be divided, because that offends the gods. And this is pretty wacky stuff from a modern perspective. It sounds crazy. And by the way, this is another misconception I want to clear up. When he says elements, these are not the elements we're talking about. So Aristotle did not discover elements. Aristotle did not come up with the idea of elements. This is not elements as you and I know it as modern people. This is like the earth, the air, the fire, the water, those kind of elements. When we say someone was exposed to the elements, like, ooh, you got caught out in that thunderstorm and had to stand there for an hour while you were waiting for your ride, you were exposed to the elements. Yes, you were. Not the kind of elements we use in chemistry. So it's a totally different idea. This does not lead naturally into the modern concept of elements. Well, like I said, Aristotle, he did good PR and he wrote a lot of stuff. And if you do good PR and you write a lot of stuff, guess what? It survives. And you become influential. One could perhaps see analogies to our contemporary legal or political system, that if you spout something long enough and loud enough, eventually somebody will believe you. I've actually heard that espoused by a politician. If you say it long enough and loud enough, eventually they'll believe you. Well, Aristotle said it long enough and he said it loud enough. And so for a very, very, very long time, the views of Aristotle hold sway. And we have the rise of what's called alchemy. Now, alchemy is this school of thought. The alchemists were people who practiced alchemy. So alchemist is not an individual person, it's a group of people. And the alchemists take all these philosophical ideas, a lot of them from Aristotle, a lot of the stuff about the elements, they mix them with religious ideas, philosophical ideas, spiritual ideas, almost artistic ideas. If you read any of this, if you go to some original sources, It's fascinating stuff. It's very, very weird to a modern audience. I mean, it's weird. They think, because remember, Aristotle says this cup is made of equal parts earth and water, or earth and fire. Well, they figure that if you have something that's made of earth and water, if you add fire to it, you can drive off the water. So they do all these things with manipulating substances. And their big goals are turning what are called base metals, so really think ugly metals, lumps of lead, into gold, and finding the secret to eternal life, finding the philosopher's stone, finding this, there is this promise, and you can see it in a religious lens because it very much exists in a religious lens, this promise of some better thing that will come. If they keep working hard enough, if they keep manipulating the elements, if they keep at this pursuit of knowledge, they will reach enlightenment. They will reach a better state. This starts in ancient Greece, pretty much with Aristotle. It continues for centuries. So it goes through, there's the golden era of Islamic cultures, which are early common era, and these alchemical ideas flourish there. Actually, the word, anything that has an al, like algebra, alchemy, caramel, probably comes from the Arabic. And alchemy, comes from an Arabic root. I don't remember the root, but they travel through Asia. I mean, you have a rich civilization in a lot of Asia at this time. I mean, China's got ancient civilization. And then they continue to evolve in medieval Europe. And really the height of sort of European alchemy, which is what we think of when we think about alchemy, is like, 1400 to 1700. So what would that be, like late medieval, beginning of the Renaissance? You're still dealing with alchemical ideas. So we have all this time, like really a lot of time. And people are still playing around with lead and, but lead, all elements are made of equal parts mercury and sulfur, and by manipulating them with other elements such as water and fire and earth, we can transmute them into precious metals, right? You all know that, right? Like, just from the get-go, you know that, right? Lots and lots and lots of time. And it's really, it's an Aristotelian world at this point. There is no what we would call true material science being done. Everything that is wrapped up in science is also wrapped up in the supernatural, which is any set of religious beliefs can be described as supernatural because they go beyond what can be described naturally and materially in the world. So, there is no separation of the supernatural and the material here. It's people just going along and, trying to turn lead into gold. So, this continues. And you might think that this continues for a long time. And nothing that we would recognize as a modern scientific way of thinking intervenes here. It's all of it is wrapped up. It hasn't been separated out. Well, then something happens. And this is where I always wish that I could just call on somebody in social studies. I want to like tag team them in on this. Because I believe Enlightenment, when is the Enlightenment pegged as starting, really? Renaissance is like mid-1700s, right? And Enlightenment is end of Renaissance? Am I correct on this? Okay, I didn't take AP Euro. Some of you did. So feel free to correct me on my timelines. But there's this thing that happens in Europe specifically in the late 18th century, late 1700s. sometimes called the chemical revolution, sometimes called the scientific revolution. And suddenly, a lot of people are now attempting to separate the philosophical and the supernatural from the material. And it's talked about as the boom in quantitative chemistry. So thinking back, quantitative means what? What? Numbers. So this is really a boom in people doing careful measurement, which none of the alchemists were doing the kind of careful. Now, the alchemists, I should say, did invent devices that are still used. Distillation apparatus. A lot of lab glassware actually comes from the alchemists. I mean, they developed, because they were so interested in manipulating this stuff, they developed processes that are still used today, but there's also a lot of garbage there. But suddenly we have people who are measuring carefully, and we have better tools for measuring. And during this chemical revolution, I gotta say, this is the province of rich white guys playing metaphorically in their mom's basement. Okay? This is a period where scientific work is being done by those who are wealthy enough to be educated. And education at this point is very much the province of a very few. You know, education costs money. So unless you're born into the nobility, basically, in Europe, you're not getting an education. You are going to be a peasant who is slogging from dawn to dusk until you die at 45. You know, crippled, hobbled, and a grandparent. Pretty grim, really. But you do have this, and in this case, it is male, it is upper class, it is white European. But they're the people who have the liberty to play around with these ideas, and they're the people who have the education to play around with these ideas. So it really does, this chemical revolution happens across Europe. And you came up with names, a lot of you, with Lavoisier and Proust, and nobody stumbled on Avogadro yet, but we'll talk about him. These are the people who are doing this stuff. And a lot of people are suddenly working on the same ideas. A lot of people are suddenly taking careful measurements. Like, here's a weird thing. If you take a chunk of iron and you heat it up, it actually gains weight. 4 minutes and we'll pick up. So we're back. And it is within this context of lots and lots and lots of people, and yes, mostly male, mostly nobility, doing lots of observations, lots of careful measurement, that we have 3 laws that are proclaimed, 3 laws that are published. So let's talk a little bit quickly about the difference between a law and a theory in science. A law doesn't explain anything. A law does not explain a single thing. And I had a great cartoon drawn by a student last year, which was this little piece of paper that says law, and it says, oops, I'm a law. I don't have to explain anything to you. Because a law doesn't explain anything. It just describes an observed phenomena. So, the law of gravitational attraction. We don't know why it works. We know that the Earth finds you attractive. We know that if you step out into empty space, you will fall towards the center of the Earth. We don't actually understand why. And the law of gravitational attraction just describes how it works. It doesn't explain anything. Hypotheses explain things. And hypotheses that have been repeatedly supported by evidence end up sort of transmogrifying into theories which explain how things work. Laws don't explain a thing. But as a result of all this careful measurement and all this work and all this effort on the part of all these, you know, sort of wacky science guys playing around on the back of the family estate, we end up with 3 laws being published towards the end of the 18th century. And the first of those is the law of conservation of mass. And this is typically attributed to Anton Lavoisier. He is French nobleman, and, you know, which is no surprise based on the fact that if he wasn't, he would be pulling a plow someplace and dying early. But a lot of people had seen the same things that Lavoisier was seeing. He's very often cited as the father of modern chemistry. He published one of the first really comprehensive books on chemistry. All that the law of conservation of mass says is matter never goes away. Matter is never created or destroyed in any kind of ordinary chemical reaction or a physical change. So if you have matter that gets added to something, or mass that gets added to something, something else has happened. So back to that thing that had been observed, that if you take a piece of iron and you heat it up, it gains weight and changes color. That's weird. Enough people had observed things like this that the discussion was going on about what is happening, because that seemed odd. And what conservation of mass says is, no. Everything that was there in the beginning is there in the end. And one of the things that really gets them to this, and I think the thing that Lavoisier publishes, is heating a mass of metal in an enclosed container. So sealing a container and heating that metal, massing the entire sealed container before you heat it and after you heat it, and the mass doesn't change. But yet if you take a piece of metal out in the open air and you heat it, it gains weight, gains mass. What's happening? So you as modern people, you know what's happening. What is it? Anybody ever seen a car with a rust spot? Okay, what is rust? Yes, it's oxidation. It's iron that has gained oxygen. Oxygen has gotten attached to it. It forms iron oxide. Well, guess what? You've just added mass. If you heat a chunk of iron in the open air, it most certainly does gain mass. Guess what mass it gains? The mass of the oxygen that just attached to it. But if you seal that up in a closed vessel and you mass the whole vessel before you heat it and you mass the whole vessel after you heat it, the mass of the vessel doesn't change, because the oxygen that's in there with the iron is what gets attached. So it's Lavoisier who finally says, hey, you know what? You're not creating mass. You're not able to destroy mass. It just changes forms. It joins with other things. It is exchanged between stuff, which seems so obvious to us, and it's really pretty revolutionary at this point. So that's the first of these big physical laws. The next one is a little bit, well, it's weirder. We're not to the really weird one. But it's the law of definite proportions. And this one is usually attributed to Proust. Proust. And the biographical information on him is not so important. But what this says is that if we take a chemical compound, if we take these pieces of iron that have been heated, and we take any two of them, we can separate them out into the same things. There will be some gas and there will be pure iron. And it doesn't matter how big the sample is. It doesn't matter where the sample came from. This starts to get to that idea that there are chunks of matter. Because up to this point, there has been no experimental evidence for, going all the way back to the idea Democritus had, this idea that there are chunks of matter. And we're still dealing with these Aristotelian notions of continuous matter and all the elements mixed together, blah, 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 blah. So this starts to move us in the direction of thinking that there are chunks. Now here's the really weird one. So these two get an English school teacher named John Dalton thinking. And what John Dalton proposes, and these are, he proposes the law of multiple proportions. And the law of multiple proportions is by far the thorniest and most complicated of these three physical laws to understand. I mean, read that for a second, and this is directly from your textbook. If two or more different compounds are composed of the same two elements, then the ratio of the masses of the second element combined with the certain mass of the first element is always a ratio of small whole numbers. What on earth does that mean? That's incomprehensible. It's terrible. So if we look at this, I mean, what Dalton's saying here is critically important. It's just really hard to understand. So if we think about the example there, which is carbon monoxide and carbon dioxide. The way it's typically expressed is really pretty incomprehensible. But if we take a chunk of carbon monoxide, we know that there are 12 grams of carbon, and that can be separated out. By this time, these folks were getting pretty good at separations. So a lot of substances, if you heat them, for instance, you can drive off the oxygen. You can collect the oxygen. Oxygen was known at this point. So if we drive off the oxygen, we're left with just carbon, just black powder. And we know that they would have probably not been able to get 12.01, but 12 grams of carbon, 16 grams of this oxygen gas. Well, if we take this other compound that's also made of carbon and oxygen, this other gas, and we separate that out, we still get 12 grams of carbon, but we get twice the amount of oxygen, which starts to again point to the idea that there are individual chunks of matter. You know, it's never 16 grams of oxygen and 18 grams of oxygen. It's always these ratios. It's always whole number ratios, which starts to point to individual pieces. So this is really revolutionary. And it's these three laws, really, that caused John Dalton to propose what is considered to be the first atomic theory. So it's typically cited as being in 1808. It varies, 1803, 1808. But to explain, because remember, a law does not explain anything. To explain those three laws, Dalton says, okay, here's the deal. All matter is made of pieces. And he uses the term atoms as sort of an homage to Democritus, as sort of a tip of the hat to a Greek who a couple thousand years ago first suggested this idea philosophically based on no experimental evidence. He says all matter is made of these pieces, we call them atoms. Now, he says that any element, for any given element, for carbon, for oxygen, for iron, for gold, the atoms are all identical. They have the same size, the same shape, the same mass. He also says you can't create them, destroy them, or divide them. So he's really, he's in line with this Democritus's idea, which is philosophical, remember, not scientific, that they're indivisible. Furthermore, says Dalton, oh, hey, I even put that on the slide. Anytime that you have a compound, it's just atoms of different elements that are combining, and they always combine in whole number ratios. Because remember, he says you cannot divide an atom. And he says all a chemical reaction is, it is atoms of different elements combining, separating, or being rearranged. That's all that's happening, folks, which doesn't sound revolutionary to us at all. But remember, it's hard to pretend you don't know what you already know. So at this point now, in the very early 19th century, we've had a flourishing of scientific thought. We've had the Enlightenment at this point. And we suddenly have really almost an intact modern atomic theory. Dalton's theory pretty much stands today. There are a couple things that we now know he didn't have. Two different big changes. So Dalton said you couldn't divide an atom. We know you can divide an atom. We know about subatomic particles. We can even divide subatomic particles. That's outside the scope of this class. But you can divide atoms. Once you do that, they're no longer atoms of that thing. So even like bigger atoms, you can break apart. You can split an atom. We've done it for weapons. We've done it for energy. But it changes its identity. And we also know, and he didn't, that you can have different masses for the same element. So carbon 12, carbon 13, carbon 14 is an example. And those are called isotopes. We will start to talk about those when we do the chapter 3 work. So those are that's not bad. For somebody who was coming from where he was coming from, that's pretty darn sharp. This guy was a school teacher. And by the way, and a lot of you mentioned this, he did study color blindness. Color blindness is still sometimes called Daltonism. And he studied it not because his brother was colorblind. Dalton himself was colorblind. So, just a little interesting factoid. Okay. So, we now have a modern atomic theory, but there are still questions about what's inside that atom. Surely the atom can't be all there is. So the electron was the first subatomic particle that we figured out. And there's a good reason for this. How many of you have ever gotten shocked? Okay. Wool socks on a wool carpet on a winter day, touch a doorknob, or maybe touch a plug for something or stick something in a light socket. I hope not. You've gotten shocked. You've seen electricity travel through the air. Yes? Anybody here ever seen electricity travel through the air? Yes. Lightning storm? Okay. So what is electricity? It's real simple. It's just the flow of electrons. That's all electricity is electrons moving. People have been aware of electrons moving since long before they thought about atoms, because we see it, we experience it all the time, long before we harnessed it and made it work for us, which is running this whole economy we're sitting in. We were really aware of the movement of electrons. So this thing here is called a cathode ray tube. Now, if you had a picture of something in your presentation that looked like an old TV, that in it. That is a cathode ray tube, but it's not the kind of cathode ray tube that we're talking about. This is sometimes called a Crookes tube, and it was it was a science toy. So we go from chemistry being the province of nobility. We have a much more sort of egalitarian playing field by this point in history. By the later part of the 19th century, even by the mid-19th century, there start to be ways for people who are not born to the nobility to advance, to get an education. Things are getting better for the masses in general, and a lot of that comes along with the Enlightenment. But there were ways in which science was still a party trick. And you have a lot of work being done with gases for, there are people who want to do research, and because they're not coming out of the nobility and they don't have money to just independently fund their little lab on the back of the estate, they have to find patrons. They have to find people who will fund their work. And so science is used as a party trick. And it's more than a party trick. But, things like the Royal Chemical Society put on lectures where they invite that nobility who used to be doing all the research to come see the interesting things we do. Because if it's fascinating, people will pay for it. And so these things had been sort of bandied about and played with for a long time. It's a really simple tube, okay? By this point, you can get electricity to flow someplace. We've sort of like halfway harnessed electricity, and you can get current. If you take this object, and what this object really is a glass tube. You could make one in here. It's a glass tube that all the air has been sucked out of. So there's very little gas left in there. There's very little in there. It's almost a vacuum. And you stick anywhere 2 electrodes out of it. And this could be 2 pieces of wire. This could be 2 nails. And then you hook up some voltage to it. And for the life of me, I can never remember which is the anode and which is the cathode. The cathode is the positive and the anode is the negative. That doesn't matter. But you run current through this thing. And remember, there's nothing in here. Suddenly, this cool line appears. If you put a little backdrop on this thing, it shows up really nicely. You put sort of it's a phosphorescent background, in fact, is what it is. But if you put this phosphorescent background in there, you get this brilliant line inside this empty tube. It's like magic. It's really cool. And it's been observed in labs all over the place. And at this point, you know, by the mid-19th century, I mean, people are doing some serious chemical research. Nobody knows what this thing is. You know, so it's like one of these brain teasers. Nobody has an answer. What is this thing? I don't know, but it's really cool. Look. Zzz. We tried to make these one year. I had a student whose father owned a sign shop, and so he had a high voltage step-up transformer. So it's something that you plug into a wall that's giving you 110 volts, and it steps it up to about 15,000 volts. And I found instructions online for making homemade cathode ray tubes. So I thought, sure, what could go wrong? Let's do it. Nobody died, so that's the positive. Notice that you are not doing that in class this year. It didn't work very well, and honestly, it was terrifying. But, like I said, nobody died, so it's all well that ends well, right? You could make a cathode ray tube, and you just need some kind of voltage to run across it. Let's get a picture of what this actually looks like. So looking at that video, when the negative end of a magnet was applied, this stream bent away from it. So we know, number one, it's affected by a charged object. So we know, number one, it has a charge. And we know that its charge is negative because it's repelled by a negatively charged object. This is what J.J. Thomson did, because he was puzzled by what the nature of this thing was, this glowing light. Now, the part that video doesn't address, so he knows that it's charged, but he still doesn't know if it's just some form of energy or if it's an actual physical particle. I would like you all to hold up an actual piece of paper somewhere near your face. Now, move it without touching it. Why does it move when you blow on it? Let's think back to physical science. What does it take to accelerate an object? A force applied and some mass, F equals ma. So there's a mass involved. When you blow on that piece of paper, are you touching it? Are you hitting it with a physical object? Yes. Yes, you are. Your breath. Your breath is a physical thing. Your breath is made of particles, of atoms, of molecules. You are moving those objects. In order for something to move, it has to be hit by something that's got mass. So, what Thomson did, he had a different setup for this. And in the other setup that he had, there was a little paddle wheel. So it's a little tiny object that looks literally like the paddle wheel on a boat. If you've ever been down to the Gateway Clipper in Pittsburgh, an actual paddle wheel, tiny little metal paddle wheel with these little paddles. And he places this little tiny paddle wheel into the cathode ray tube. And those cathode rays hit the paddle wheel, and guess what they do? They move the darn thing. So if that cathode ray can strike an object and move it, what does that mean about what that cathode ray is made up of? Is it just some massless form of energy, or does it now have to actually be a thing that has mass? It has to actually be a physical object that has mass. So this green glowing light is not just some form of energy. It actually has mass. It's a physical particle. And this, again, this doesn't sound all that revolutionary to us. Okay, great. So what does J.J. Thomson really find with all of his playing around with cathode ray tubes? He finds that there is a particle that is negatively charged. And what does he find out about its mass? That it's teeny, tiny, tiny, tiny. He determines a mass-to-charge ratio and finds that this thing is a 1/2000th the mass of hydrogen. Tiny, but it has mass. No matter how small that mass is, it has mass. And this is huge. So suddenly, we know that there is a piece of something inside these pieces that we didn't think could be divided. Thomson takes all this, and you have seen in your research a bunch of different years associated with Thomson's work and with Rutherford's work. The reason for that is someone may conduct a set of experiments in one year, but then think about them for a while. And Rutherford especially is notorious for this. Like there are experiments that were done in, 1905 or 1907, and Rutherford doesn't actually publish anything on them until 1911 because he was a notoriously slow thinker. Awesome thinker, but he took his time. The man carefully considered all the angles. So Thomson was doing this work over a number of years, and very often the date for when something was suggested is the date it was published. So what Thomson finally comes out and says is, okay, I have found negatively charged particles that reside within an atom. Now we know that atoms are neutral. They are not electrically charged. So, how does this work if I found a negatively charged particle? What he suggests is a model of the atom in which the whole thing is just this ball of positive charge, and scattered throughout it, like raisins, like blueberries in a blueberry muffin, are these little negative areas. And he actually, and I think many of you probably ran across this, Thomson names them corpuscles, which I think it's a real shame that that's not the name that's stuck. But they end up being called electrons because already it's understood that they're involved in the flow of electricity. So, hence, electrons. This model is the plum pudding model. So this is the plum pudding model where Thomson comes up with a way to sort of have his cake and eat it too. Have a neutral atom, but have these negative physical particles that are part of it. It's as reasonable as anything else to date. And this one just kind of recaps what we've done. He did believe it was caused by a stream of particles. The stream could be blocked, and it could move an object, which proved that it had mass. And it was deflected by a negatively charged object. So it was proved that it had negative charge. And that's Thomson in his lab. Thomson was a fabulous experimentalist. He was famous for building really pretty awesome apparatus. So it's 1897 and he finally publishes his so-called plum pudding model. And, it doesn't do anything to anything that Dalton has to say, except that there is something smaller than the atom. We can divide the atom. And it doesn't change, Dalton's essential idea that there are these little spherical balls called atoms that can't be divided. Thomson's work doesn't change that. We're still looking at these little spherical balls. Now they just have little points of negativity embedded in them. Okay. Now, Thomson, and you probably ran across the word Cavendish Lab a whole bunch of times. So the Cavendish Lab is at Cambridge University in England, and the Cavendish Lab was a hotbed of particle physics. They did amazing stuff, and science works socially, just like your social brain helps you work. All of these scientists were working together and discussing ideas, because that's what we do in science. We discuss ideas. And Thomson was really quite good at bringing students in. And one of, well, before we do that, Robert Millikan, who was an American, he was from Iowa and working at the University of Chicago. Thomson says electrons have mass. Millikan actually figures out the individual mass of the electron. He does what's called the falling drop experiment or the oil drop experiment. And he basically uses classical physics that you can figure out how much mass something has and how much gravity is working on it to figure out how fast it falls. And he electrifies those little tiny drops until he can suspend them by repelling them with an opposite charge. And by figuring out how much charge is needed to counter the force of gravity, he can actually figure out the mass of the charge. And he does this with a bunch of different materials, whoops, thereby figuring out that electrons are universal for materials. And he does figure out the magnitude of the charge as well as the mass of the electron. And they're pretty darn little. So you understand the difference between an observation and an inference, I think. But I'll refresh you. An observation is just information you've gotten from your senses. Once you start to say what that means, once you start to interpret that, you're into the realm of inference. So Thomson says, hey, these electrons are tiny, tiny, tiny little particles, and they're neutral. There has to be something else that accounts for the neutrality of the atom. I'm sorry, they're negatively charged. Something else has to make the atom neutral overall. Thomson, of course, is still working on the idea that it's just a soup of positive charge. But the other big thing is, what accounts for all of its mass? If these electrons are so tiny and they have so little mass, how can things have mass? How does this bowl have mass? What's making it have mass? These are questions that sound odd to us. It just does. But if you're working in the particle physics field, you'll want to know why. Oh, shoot. What they proposed was that instead of this big sphere of positiveness with just little bits of negativeness around it, in fact, there was some tremendous center that was dense, densely positive, so that when a positively charged particle, such as an alpha particle, hit it, it would come straight backwards. This leads to what's called the planetary model. It's called the Rutherford model sometimes. So the first, and this is the symbol that we see frequently. This is the symbol that you see on stuff. That's the symbol for the planetary model. It's that little positive center with all those loops coming out around it, with little electrons on them. So it's modeled on a solar system. You have a little positive sun and you have all these little negative planets circling it, except it's not as though they're in neat orbits, you know, stacked inside one another. They're just all sort of spinning around in space. It's great. What couldn't be explained was why the electrons didn't get sucked into the nucleus. So they're negatively charged. The nucleus is positively charged. If you have a negatively charged particle and a positively charged particle, what should happen? They should be attracted. And there's all kinds of other stuff, but why don't the electrons just get sucked in? So a word about how to organize your information. There are really two ways to do it. You can organize it in straight chronological fashion. You'll notice that that's not exactly what I'm doing here. You can also organize it by influence. So thus far we've talked about Dalton, who's kind of unconnected to these other guys. We'll pick it up tomorrow.